Hi everyone, it's Emil again. Today we're going to go over doing a DFT+U calculation. In particular, we're doing LSDA+U. So, when wanting to do, for example, LDAU type 1, the rotationally invariant DFT+U introduced by Lichtenstein et al., you can adjust the U and J tags. The J is calculated in one way and the U in another. You can calculate the U just with VASP using LDAU type 3, linear response of Coccocioni et al. I hope my Italian is good. I took Spanish for 6 years, maybe 4, 5, split the difference. So, VASP has a handy little tutorial on how to do this. The trick is, you're treating the first atom. For example, if you're working with nickel and oxygen, you have 3 groups. Nickel 1, atom 1, remaining of the nickel atoms, and then oxygen. So to trick, quote-unquote, trick VASP, you're doing 2 different U, or Ni potentials, right? Nickel. In my case, I'm doing uranium. So how do you do that? Well, hot create, just like that. And now I have a bunch of different other things here, but that's because I have to restart the calculation. I end up doing a mistake, and now we're rerunning it. Now if you look at the in-car, it's very bare bones. Alright? You have the K points, whatever. Bosscar here, accurate precision, EDIF, I smear 0, sigma, I spin is 2 because you're doing a magnetic calculation. This case is anti-ferromagnetic on the tutorial, and in my case, it is ferromagnetic. I smear 0, sigma 0.2, L over is 11, L max mix is 4. 4 corresponds to the F electrons, but when you actually do the DFT+U calculations, they're going to be 6. So, I'll just save that. I'll run sbatch job, and I'll watch it finish. It shouldn't take longer than roughly a minute or 2, and we'll just sit and wait. Go. So this took roughly 15 minutes or so to converge. Now the trick is you want to, you have your charge car, you have your wave car, right here. So now I'm going to go into this directory that I already have set up, and you'll see why I have it named as such. I'm going to remove the previous wave car, charge car, pro car, and charge, because I had made an error. I'm also going to remove the previous boss car. That should be it. So now from the ground state that I had before, the ground state directory, I'm going to import the in-car, right, the boss car, everything, just for clarity's sake. You also want the charge car and the wave car. I think that's pretty much it. So what we're doing next, after the DFT ground state, also it helps to look at this. So let's go back to the ground state, and let's look at the out car. So for my particular case, I'm working with an F. The F orbitals, you see how they converged. Non-magnetic, that's a problem. Is it? Why were they not ferromagnetically ordered? the in-car was set up for... Okay. This might be okay. Well, the ground state, it's assuming, is non-magnetic, which shouldn't be the case. But, anyways, what are you gonna do? What's important here is to grab this 8.439, I believe. No? Where is it getting the 4.438? From here. So running it by 2. So in our case, we want to keep track of, I believe, that value. So I have a sheet here. Let's name it U. Ground state. F is going to be 2.842. I believe. I'll double check this at the end. So if this is 8.438 or 8.439, number of d electrons. So they're using 4 here instead of 8. I'm not going to be too concerned just yet. Yeah, I won't be too concerned. Just double check that everything was done properly. In-car is ferromagnetic, 0, fine. F electrons are there. Now revert back to here. So in this in-car, right now I'm dealing with the non-self-consistent response. And in this, they set the following parameters. LDA+U, LDA+U type is 3 to calculate U, as we mentioned before. LDA+UL is dependent on the species. So there's 3 species here. In particular, I believe it's nickel 1, nickel 2, and oxygen. The -1 means you're not going to apply the correction. LDA+UL. Right? -1, no on-site interaction. L is the quantum number. For my case, it'll be 3 for uranium, because I'm dealing with the F orbital. So let's add the following. LDA+U equals dot true. LDA+U type equals 3 because we're calculating for U. LDA+UL equals 3 minus 1 minus 1. So we're not applying it to the second uranium, nor are we applying it to germanium. LDA+U equals 0.100. LDA+UJ equals 0.100, as is in the tutorial. And I charge is going to be set to 11. Again, be sure to use the charge density from the ground state DFT calculation that we just did. Okay, so this is pretty much it. And we copied job, wave car, charge car, in-car, box car, everything. Okay, so now I'm going to run dispatch job, and this shouldn't take too long at all. I see. Okay. So this is important. In the charge car, I end up missing the following: 1, 3, 8. Okay? Because you're treating them separately. So it looks like I'll have to redo this. That's okay. That's fine. That just means we have to redo the ground state. Type of information is not consistent with the number of types. Okay. Maybe that's why. But actually, I don't want it to read the wave car or the charge car from before, as I don't want that to interfere, I should say, with the magnetic ordering. So let's do this one more time, and it's good that I have everything. I have all the errors popping up now, so you guys can see where I'm going wrong. And that's okay. So we're redoing the ground state again, and then we'll move on to doing the ground state. Or I should say, excuse me, the non-self-consistent response. In this case, the ferromagnetic ordering should be hopefully correct, but we'll see. And go. So as you can see, wave functions are written. Hopefully it's good. Let's take another look at the out car. And there we go. Our uranium is ferromagnetically ordered. I'm going to write down 1.589. I think that's what's important here. Again, not entirely sure. We'll find out. So now you want to go back to this part. Copy. Ground. From the ground. Wave car. Your charge car. And charge, just in case. I don't know, maybe. Now, I'm going to double check the in car. Make sure everything's fine and dandy there. Okay? Same exact things. I charge 11. Right? Let's have S-patch job. Let's monitor it. I think this part should only take about 30 seconds or so. Whereas the initial ground state optimization takes maybe 10 minutes. If you set it to EDIF -6. I don't know why this keeps coming up. Maybe it does take a little longer when you do it correctly, who knows. On and go. So, this was considerably shorter. I'm going to look back at the out car now. And we have values for the F electrons of atom 1, 1.653. How am I going to put this down? Okay. Levitt said it's non-self-consistent field 1.653. So now, as pair following, right? Hence, x11 equals, x11. This equals this. So how do we set up that part? Well, it's pretty much the same thing that we just did here with U.1, J.1. The only charge is we're going to not set I charge 11, so the charge density can change. So I'm going to move to the old directory. I'm going to make a new one called SC. Okay. Change directory to SC. From NSC, I'm going to copy over the wave car. It's going to speed things up. So we don't need the charge card because that's changing already. So we don't want to start many things. We're gonna get the POS car, the pot car, the in car, key points, and the job file. Alright. We're gonna go back to the in car. We're gonna comment out iCharge equals 11. Just like that. We're gonna do SBatch job. See how it goes. Okay, wave car is red. It's gonna change the charge. Alright, and there's our wave functions written. Now let's go to the out car. Atom 1, F electron there, is going to be a 1.614. Right, which is a little... I wouldn't be too concerned, I guess. I mean, there is... No. Anyways. Double check the POS car. Okay, that's why. You gotta be careful. You have to be careful. Okay, because again, 4 and 8. Okay? You have to be careful. I'm clearly not careful enough. I have to redo both of these. Alright, so that's a non-consistent field. To the self-consistent field, do the same thing. I'm going to copy the POS car and the pot car from the ground, because like I said, atom 1 has to be different. We're treating it like its own little thing. So we're gonna have to, and really I should have known that, I guess, from the beginning. It's reading the wave car. I don't know if I want it to really read the wave car. We'll see if it's different at the end. And regardless, we're gonna redo this same process for different iterations of U and J. So we'll see what happens in this out car. Okay, this is much better. 1.883. Okay, for the ground state. 1.883 for atom 1. Now we have a negative 2.3. Oh no, excuse me. 2.94 electron volts. Now, we go back to the self-consistent field. Okay. From the non-self-consistent field, we're copying the wave car. We're going to move the charge car. We don't need the charge car again. Okay, we're going to look at the POS car. 138. Good, it's fine. Again, it's good that you're seeing where I mess up. It's good that I'm messing up. Because when it comes to VASP, it's very easy to make very silly mistakes that will ultimately affect your results. Okay, so SCF1, same thing. One. Alright, so our self-consistent field has finished up here. Let's go back to the out car. Now we have something that should be greater following. So we have 1.638. Bring this back up. Type in 1.638. We have 0.49 electron volts. Let's look back at this. Okay, they report 0.012. They report They report 0.12 electron volts, the self-consistent field, and for the non-consistent field, 0.5 electron volts. So roughly 5 or so orders of magnitude, which is roughly the same thing we see here. So this lets me know that I'm more or less on the right track. And so we repeat this for values of minus 0.2 to 0.2 electron volts set to LSDA+U and LSDA+G. So that's what I'll do. So we're going to start with the non-self-consistent field set to 0.2, 0.15, whatever. Copy the wave car and copy the charge car and the wave car. No, copy just the wave car over. Okay. Make sure the pos car is all the same. So let's run one more together. Let's make a new directory called NSC 0.15, 0.15. From NSC, I'm going to grab job, K points, pos car, hot car, in car. From the ground state, let's see, non-self-consistent, charge density, and wave car. Okay. From the ground, we're going to get the charge car and the wave car. Now let's look at our in car. We're going to change this from 0.1 to 0.15. Again, look at the pos car, make sure it's alright. 138. Scratch job, tail, F out. And we'll be right back. Go. Alright. Again, it's pretty quick. Let's them the out car. Now for 0.15, our first uranium atom is going to be 2.039. 39. Compare that to the ground state. Copy this over. Right? Same exact format. Now, let's have a new directory, self-consistent, 1.5 and 1.5. Change directory to the 1.5. Okay, and again, we're doing the self-consistent response. Let's copy everything over from the initial self-consistent. Job, in car, pos car, hot car, K points. Now what do we want from our non-self-consistent 1.5 that we just pulled out? Speed things up, good idea to restart this calculation from the wave car. So, from the non-self-consistent 1.5, we need the wave car. Now you check the in-car. 0.15, iCharge is no longer, it's commented out. It's commented out. Okay. And that should be all fine and dandy. Alright. Now we have our workflow set up mentally pretty well. And go. Alright, so again, wave functions are done here. Let's look at the out car. For our self-consistent field values are going to be, for the F electrons, that is 1.653. So, let's copy this over. Make sure it's the right cell. Good. Okay. So this is our, maybe it's better to say, actually, that's 1.1, this would be 0.15, maybe? No, I'm not sure. Anyways, we'll just have it set up here. 0.15, make sure you guys take notes. If needed, just do some slight formatting changes here. This to be on the right. Maybe the left. This should not be merged actually. Probably blank. Okay. So these are our values so far. I'm going to continue now. I'm going to do the same exact process, okay? It's literally just going to be, okay, since our ground state is done, we're going to do a non-self-consistent response. Copy the charge car and wave car from the ground state. You're changing these from 0.1, 0.15, 0.2, 0.05, 0. 0? So I double checked, and for clarification purposes, it's actually not the magnetization here. It is the total charge of the ion, particularly the first one, again. So I just compiled all the results, and I have a U Hubbard correction value of 2.01. And this makes sense. I'm looking at the exact same trend, roughly, and simultaneously I'm also looking at an appropriate plus B value. So that pretty much wraps it up. In the next video, I'm going to be doing an actual DFT+U with the corrections on a uranium compound, particularly uranium germanide. This is, yeah. So again, thanks for watching. Any questions? I know I had a couple of hiccups in this video. Please feel free to comment down below if anything's unclear. Again, the VASP website does seem to be a good tutorial, but there are still certain things that are, I should say, not really unclear, but they're unclear.